So why use cross sections? Um, Cross sections are low tech. That's one of the major reasons to use a cross section. By a cross section, I mean if you are in the river and you are looking downstream, it is measurements of the bed elevation as you move all the way along the river, kind of perpendicular to flow. And you can collect cross sections through various means that are very low tech. If you have just a pin set on both sides of the channel, you can stretch a tape across and then you can measure the depth down from that pin. And even if you don't know the elevation, even if it's not tied into any sort of national elevation datum, you can still repeat the measurement over time at that location and see how the river has changed. So you could be very low tech. More recently, we tend to use more sophisticated methods. Probably in your surveying classes, you use total stations and rods. You can also use echo sounders. So somewhat similar to the ADCP that we talked about, it uses sound, and it's the time it takes the sound to bounce back up to the receiver. And you can get very sophisticated, but at the end of the day, they're all cross sections. So you can compare the old data to newer data to very new data, and if you're at the exact same location, you could have comparable data. Here's an example. This is on the Missouri River. It's a survey done in 1940, and we've got these depths, but they're collected as cross sections, so perpendicular to the channel. They're depths below a defined water surface, and so I have gone back and digitized some of this information, and I can compare it to more recent information, and we can see how things have changed over time. There's a lot of historic data that's been collected as cross sections. Economy. So if you're doing something, like this, it can be done very inexpensively. And even if you have more sophisticated equipment, the time it takes just to get one cross section across the channel or a few cross sections is pretty modest. So they're less expensive than more distributed kinds of surveying methods. Visualization is a plus for cross sections. So what did this channel do from 2009 or 2000 or from 1997 to 2009? Um, well, it looks like perhaps the channel widened. You can tell right away that the channel widened. So you can visualize very easy. Now, a caution when you are looking at cross sections, very often the elevation is distorted. The scale here is 5 feet and the scale here is 500 feet. And so you might get the idea of what the cross section looks like. If it was a non-distorted scale, it would look like this. This is actually a very wide and shallow kind of cross section. So just be careful with the distorted nature of cross sections. There's computations, simple computations with cross sections. So in this example again, if you're looking at the top width and it was 1,260 feet, and then in 2009 we look and it's 1,360 feet, well, you can tell very easily that, yeah, it widened by 100 feet. The devil's in the details. We'll talk about that in a minute. You could look at the lowest point in the channel pretty easily and say, well, that invert changed by 2 feet, dropped by 2 feet. You can also do math on the whole cross section to look at average bed change, which we will talk about in a minute. Hydraulic equations. So an equation to estimate the discharge in the channel uses the cross-sectional area and the cross-sectional hydraulic radius, which is the area divided by the wetted perimeter, or the boundary of the channel that's wet. And these are both based on cross-sectional measurements. Sediment transport functions were all of them developed using cross-sectional average hydraulics and sediment transport. And so the wetted perimeter, for instance, that goes in this Meyer-Peter-Moller sediment transport function is meant to be for a cross section. And then there's one-dimensional modeling. So using HEC-RAS is the most common one-dimensional hydraulic model. And you put in your data as cross-sections. Now there has been a push in recent years and a lot more use of 2D modeling. And 2D modeling you have to build a mesh. So you need data that is more distributed. You can still start with cross sections, but it ends up being easier to start with other kinds of survey data if your goal is 2D modeling. But for 1D modeling, you still need cross sections. All right, let's talk about the computations for cross sections. The width. So the width, you take the top width is the right bank station minus the left bank station. The bottom width is the right toe of the bank minus the left toe of the bank, the stations. And you just subtract them, right? It's pretty easy. You might need to linearly interpolate. So if I'm looking for an elevation here of 788, and these are my survey points, and I don't have a survey point at 788, then I can linearly interpolate and get what the station is, or the distance along the cross section at that elevation. So this is a channel, and there are, you could say, multiple channels. There may be an island. The flow probably is splitting, going around for a while. So what is the channel width? What's the correct width of the channel in this case? Should it go all the way from this left point to this right point, and that's the top width of the channel? Or should it be this width here plus this width here, but subtract the width in the middle where it's actually dry? So which one is correct? Actually, it depends on what you're going for, what your purpose is in computing this top width. Sometimes one definition or the other will be more correct. Here is a map showing the change in the top width from 1992 to 1995 on the Kansas River. And I scaled the dots according to how much bank erosion occurred, and then put the little numbers next to them. In green dots, the channel actually narrowed, and in red dots, the channel widened. And so you can see this is the upstream end, and as we start to move downstream, the areas that the channel widened, and then as we move further downstream, mostly the channel narrowed. Okay, average bed elevation. Here's an example of that. So what would you say happened from 2009 to 2013 at this cross section? This is on the Missouri River, kind of close to where the Kansas River confluence joins the Missouri. Well, you could say that the lowest point in the channel, called the Thalweg or the invert, it lowered from 2009 to 2013, but the rest of the channel over here appears to have raised or graded from 2009 to 2013. So overall, what did the channel do? You need some sort of average. So the way you compute the average bed elevation is you take the top width elevation, and it's always the average of the channel up to some point. So you have to define how much of the channel. It might be up to bank full. Either your sort of geomorphic bank full or the true top of banks, and or it could be some other part of the channel that you're defining, but you need a top width at that elevation, and then you subtract the average depth, and the average depth is the cross-sectional area divided by the top width. Essentially what you're doing is you're saying what is the area of this channel, and then the depth of this channel if it was a rectangle that had the same width as that top elevation. So functionally, we're saying that these things are equivalent. You're finding that depth, and then the elevation, the top elevation minus that depth is giving you the average bed elevation. So your first step is to establish what your top elevation should be. The top of bank, or maybe it's a 1.2-year discharge, a 2-year discharge, is the 100-year discharge, the ordinary high water mark, which is somewhat synonymous with your channel forming discharge, maybe a little lower. And the definition should be consistent from location to location if you're looking at multiple locations, and or if you're going to average over reaches. And then also it needs to be consistent from year to year, and that's especially important. Okay, so you've established your top elevation baseline, and then next you compute the cross-sectional area from the channel up to that elevation. The easiest way to do this most of the time in a spreadsheet is with a series of little triangles or polygons. So in this case, it's a polygon. And so between every 2 points, you compute the cross-sectional area, and then you go on to the next 2 points and you add them all up. And that will give you the cross-sectional area. The equation for this area is it's the depth of your baseline, your top elevation, minus the depth at your first point, plus that top elevation minus the depth at the second point divided by 2. So it's your average now depth amongst those 2 points, times by your horizontal distance between your 2 points. So this station minus that station gives you the horizontal distance. So it's the equation for a polygon. There's another way you can do it, which you might have learned in survey class, which is a little method for finding the area of a polygon, and that works as well. And I won't go into it, but there are multiple ways to compute the area of a polygon. This would be one of them. In this case, it works pretty easily in a spreadsheet, but you can also do this other area of a polygon algorithm. Now, your first and your last points are not going to be trapezoids, but they're going to be little triangles. And I think I was calling this the area of a polygon. This little thing here is a trapezoid. It's the area of a trapezoid with a flat top. But on the corners, they are triangles. So you need to use 1/2 base times height to get the area of a triangle. Okay, so you've established that top elevation. You compute the cross-sectional area, interpolating your endpoints if necessary. And then usually with real data, it is necessary. Some of the examples I give, I may or may not, I might have made it easy for you, but in real data, you're always going to have to interpolate. You compute your top width of the cross-section at that baseline top elevation you selected. Again, interpolate those endpoints if necessary. Compute the hydraulic depth, which is the cross-sectional area divided by the top width. And then you compute the average bed, which is the elevation of your baseline top elevation minus the hydraulic depth, and that gives you your average bed elevation. So that's computing the average bed. Average bed change is you compute it for one cross section and you compute it again for the next cross section, and you subtract the average bed elevations and it'll tell you how much it changed. Okay, so here's a little exercise that you can do on your own. So these are the stations, and go ahead and copy this down, or I'll put this as a spreadsheet so you can do this part of it more easily. Try to compute the average bed elevation. You can go ahead and pause and do that, and when you're done, continue the video. Okay, so let's walk through this example. In this case, this elevation is at 730. So we've selected 730 for whatever reason as being the elevation. Maybe this is that 1.2 year discharge. And as you can tell, it's not really at the top of the banks, but this could be a river channel that is incised. And so before it had incised, that might have been the area to get to the top of the banks, and now that the channel has degraded or incised, the 1.2 year discharge might be lower. So for whatever reason, we've selected this, and 730. So we really only need the data up to elevation 730. And so I'm just going to copy that information here, and so let's see, in class exercise. Oh, looks like I've already done it. That's great. So information here up to 730 to 730. Well, I'm gonna do it again for you so you can see. All right. So here we have station. Here we have the elevation, and the equation is this one here. So I'll just paste it over here so I can look at it. And so here is the area. Okay, so this was starting right at the point. Well, let's go back to the figure. So that first the first point to the next point is going to be a triangle, right? And then after that, we've got a couple of trapezoids, and then we end off with a triangle. So I am going to compute the area of a triangle um, equals, let's see, 1/2 times the base of the triangle um, times the height of the triangle. So in this case, the uh, the base is this times the height of the triangle, which will be the depth. Okay, so that is the cross-sectional area for that first little triangle. Then we can use this formula here for the area of a polygon. And so we're going to take the y elevation, so it's the baseline elevation minus um, the y plus the baseline elevation minus the next one. And divided by 2. Yep. And then multiply by the difference um, in the stations. So this to this. All right, so that's the area. Okay, so I made a little mistake. So I've got the area of the triangle going from this station to this station, and now I need the area of the trapezoid that goes from here to there. So actually, I should put this here. So the triangle is these two, and then this one, I'm just going to drag my formula up so that now it corresponds to that trapezoid, and then this trapezoid, and then I will end up again with the area of a triangle, this final triangle, but which will be from here to there, from here to there. And okay, let's just try that again. Equals 1/2 times the base, which will be this, times the height, which will be this. Okay, so I've got a triangle, 1, 2, 3 trapezoids, and there we have it. Actually, this from here to here is a triangle, so I don't need the trapezoid there. I've just got the triangle. Okay, so you can see that even though it's not hard math, it'd be easy to make a little mistake, but my total here comes to 6,429 square feet, or whatever units I was dealing with. And yep, that's the number I have. Okay, so then this is the area, and I'll just drag this down here. The top width is the right station minus the left station at that elevation, which don't need to interpolate in this case. And so then the hydraulic depth is the area divided by the top width. And so then the average bed elevation, will be the top width's elevation, which is 730, minus the hydraulic depth. So this is the average bed elevation. It's typical to report elevations to 2 decimal places, but carry the rest of the decimals through your computations, and then at the end you can round it to 2 decimals. Okay. So hopefully that is also what you got, and we will continue. All right, if you were looking at the change in the average bed, there's some things to remember. First of all, you have to be comparing a cross section at the same location. You can't compare the average bed from cross sections that are, 200 feet apart or something, because the bed goes up and the bed goes down and channels widen and narrow as the rivers move. So you need to be in the same location, pretty close to exactly the same. You should compare a consistent portion of the channel from year to year. So if one year you go up to that 730 elevation, the next year you also have to go up to 730. You can't go up to a different elevation in each year. Now, there's a couple ways to be consistent. What I just described was being consistent in the elevation. So if the survey extends far enough that you can go to up to an elevation, then that makes good sense. That could also be the top of banks, going up to that top of bank elevation, and that's then being consistent. The other way you can do it is you can go over a consistent stations in the channel, and I'll explain that a little bit. If the channel location is stabilized, so it's not moving, and if it's not doing this, but it's really just going up and down, then you can use consistent stationing. I'll explain that more in a second. The next is consistency in cross-section to cross-section. So if I'm going to take the average bed change in many cross-sections, for instance, I'm looking for how much bed change occurred over a 5-mile reach of river, then my definition for the top of the analysis, the top of bank or however far of the channel I'm using, should be consistent from cross-section to cross-section. It wouldn't necessarily have to be, but it will be better if, for instance, you've got a smooth water surface and that's defining how high up the channel you're looking. Or like I say, it could be the top of bank or some other sort of geomorphic indicator. All right, and here are the reasons why you need to be consistent. First of all, same cross sections. If I am averaging the bed change over this reach, and I've got average bed elevations in 1994 at these magenta locations, and then in 2009 I've got much more data. It might be tempting for me to look at the average bed elevation at just these 3 locations in 1994, and then to look at all the average bed elevations in 2009, but that would be incorrect. I can only do the bed change at locations where I have data in both years. The reason is, what if there's a permanent scour hole that is right here for some reason? If I just take averages, or even if I build a surface like in GIS, using data from one year and I subtract the other year, I'm going to show some big change that's not really change. It's just based on my data sampling missing that in one of the years. So cross-section analysis, both cross-section years need to be in the same location. So you have a consistent cross-sections. The next thing is consistency in the portion of the channel that you have that you're including. So what happened from 1994 to 2013? Did the bed upgrade or degrade? I think you would say that it degraded, and you would be right. But if you took an average of these bed elevations from both years using all the data that's available, you would actually show a higher bed in 2013. So you would go from 94 and the bed would rise. And that's not real. what the reason why it would do this is because in 2013 you're also including all this extra data that's going higher up on the sides of the channel. And so you'll get erroneous bed change values unless you're looking at just the same portion of the channel from both years. So as I explained, there's two ways that you can get a consistent portion of the channel. And one of them is to use consistent stationing. So in that case, you would truncate your 2013. You would say, I don't care about any of that data, and I don't care about the data that's to the left of this point here either. I'm only going to use data where the stations are common. And this can work. This is what we do on the Missouri River for some good reasons, but there are some issues. Okay, the next thing is if you are consistent doing something like this, it can be a problem when your cross sections are very different from location to location. For instance, looking at the green cross sections, some of them are very long, and in other places they're very short. And so the bed change values you get at a long cross section that's covering a different part of the channel may be different than what you get covering a smaller part of the channel. So if you're going to average over reaches, it's better if your cross sections can be consistent in their widths as well. All right. A way that the common stations can fail epically is if your channel is widening. So if this was your channel in 1990, and then in 2015 this was your channel, if I look at just the common stations, so the horizontal parts of the channel that are common in both, I would get a channel that, or analysis that looked like this. And if I truncated 2015, then I'm getting the bank in 1990, but in 2015 I'm not getting the bank. And so I'm going to show that this channel degraded if I look at the average bed. But it didn't really. Like logically, this bed stayed the same, it just widened. I shouldn't really see the bed change much, if at all. And so this is an epic failure mode for trying to make your channel consistent by using stations. That's why it's better if you can to go up to a common elevation. If you can go up to a common elevation, then even if the channel widens or if it moves, then you'll still be okay. So here's an example on the Kansas River, a real example from 1992, and then the channel moved over a bit in 2009. And if I looked at just the consistent stationing, I would end up leaving off the bank that's here on the right side, and I would show bed change that was spurious. Okay. Here is an issue where there was a problem with reach averaging. At one cross section, we went up to an elevation of 735, and it's kind of low down in the channel. And at another cross section, 735 is sort of higher up in the channel. And so we're covering sort of different portions of the channel, and then we're averaging it over reaches. So you need to be consistent if you're going to average cross sections. All right. Consistency, the best is to have identical cross sections over time, and they're longitudinally consistent how much of the channel you're using, the sloping plane, a water surface, when the gauge reads a certain amount, and also be geomorphically relevant. So it could be the bank full, like we've talked about. Or the baseline could be geomorphically relevant but changing over time. So if the bank full elevation is actually changing over time, or the 1.5-year discharge, that would also work. But that would be two examples of being consistent. All right. Now the reason that you might not be able to do this is if you don't have data that goes up very high. And this is the case for very large rivers. I will show you later on in the lecture an example of why it is that we have maybe data that doesn't go up the banks, but only for the bed. And it has to do with large rivers and collecting the data by boat. And so we'll get to that in a minute.